Here we have a to the power of n. Because a is being raised to the power of n, we call a the base, and the n is our exponent. We just don't know what number it is yet. Let's have a look at a couple examples. What is a to the power of 1? Well, a to the power of 1 is simply a multiplied by itself once. So a to the power of 1 is simply equal to a. Where a to the power of 2, or a squared, means a multiplied by itself twice. A to the power of 3, therefore, is a multiplied by itself 3 times. So a to the power of 3 is equal to a times a times a. So we can raise a to any positive number in this manner. And a to the power of n simply means that we don't know how many times a is multiplied by itself. We could write that as a times, put in some ellipses, times a. And this repeats. We have a an n number of times. If someone tells me what n is, I can tell you how many a's we have in this chain. I want to take a quick aside and remind you what a coefficient is. So if I've just written the letter x, let me make that a little bit bigger. So if I've just written an x, and I want to compare that to 2 times x, or 2x, what are the coefficients in each case? Well, in the second example, 2x, the coefficient of x is clearly 2, the number it's being multiplied by. Well, what if I just have x? This is one of those times where we are allowed to make an assumption. If there's no number explicitly given in front of our letter, in front of our variable, then the coefficient is a 1. So that means that in front of this a to the power of 1, there's actually a 1 that we didn't need to write. But it also means that 1 times a to the power of 1 is really 1 times a. Now, I'm not suggesting you write the 1. We're still going to omit it. But I do want you to remember that it's there. So when we move on to these examples, we'll see why that becomes important. A to the power of 0. What is a to the power of 0? Well, if I'm raising something to the power of 0, it means I'm multiplying it by itself 0 times. I'm not multiplying it by itself at all. This is where I need you to remember that if there's no coefficient given, that the coefficient is actually 1. So while there aren't any a's there, that 1 is still there. So a to the power of 0 is just equal to 1. Now from there, we're going to move on to the negative exponents, and these can be a little bit tricky. A negative exponent isn't the same as a regular negative number. It has a very particular meaning. As soon as you see the negative, a to the negative 1, a to the negative 2, and so on, this means take the reciprocal. So let's do a quick discussion, have a quick discussion on what a reciprocal is. For example, what is the reciprocal of 2? Well, a reciprocal is just 1 over the number we're talking about. So the reciprocal of 2 is 1 over 2. And the reciprocal of 3 would be 1 over 3. Of course, the reciprocal of 1/2 is 2. The reciprocal of 1/3 is 3. So what you might also notice is that we're really just taking the fraction and flipping it upside down. Because here's another hidden one. 2 can really be written as 2 over 1. It's just that if 1 is the only thing in the denominator, that we don't write it. And 3, of course, can also be written as 3 over 1. So you'll notice that what's happened here is the numerator has become the denominator, and the original denominator has become the new numerator, which means that the reciprocal of 3/4 would be 4 over 3. Okay. So how does that work here? Well, here I'm being told to take a and raise it to the power of -1. In other words, take its reciprocal. So I get 1 over a. A is still to the power of 1, but a to the power of 1 we know is just a. So a to the power of -1 can also be written as 1 over a. Similarly then, a to the power of -2 means, sure, a is squared. But first I'm going to take its reciprocal. So I get 1 over a squared. I could also write that as 1 over a times a. but we're just going to keep it simple on this side. Right here, on the left side, we were just showing that a squared does mean a times a. It doesn't mean that writing it as a times a is necessary or any more efficient. Again, we can summarize what's going on here with this trend of negative exponents by looking at a to the power of negative n. Again, the negative just means take the reciprocal, so I get 1 over a. And what power is it raised to? Well, it's still raised to the power of n. So with that as our starting point, let's have a look at the properties of exponents.
Through the properties of exponents one at a time, and using the meaning of exponents that we just looked at on the previous slide, we'll figure out how to get to the answer and how, therefore, we can solve the same problem using the property of exponents. So let's start with an example. What if we have x squared and we multiply that by x to the power of 3? So we match this property. We have some base a raised to an exponent m, and we're multiplying that by, again, the base a raised to a different exponent n. What's really important here is that the base be identical. Otherwise, this doesn't work. But the fact that we have an exponent m and an exponent n tells us that while these exponents could have the same value, they don't have to. Okay, so what does this really mean? If I have x squared and I'm multiplying that by x cubed, x to the power of 3. Well, x squared is really just x times x. And then we're multiplying that, so there's that multiplication point repeated, by x to the power of 3, in other words, by x multiplied by itself 3 times. So altogether we have 1, 2, 3, 4, 5 x's all multiplied together, which we could more easily write as x to the power of 5. So x to the power of 2 times x to the power of 3 is x to the power of 5. What you might notice is that 2 plus 3 gives us 5. And that's exactly what's captured here in the property. So if we have the same example, x to the power of 2 times x to the power of 3, we don't have to write this out as 5x's multiplied together. We can simply write this out as the x once. Again, we can multiply these together because the base is the same. And then I'll take the two exponents and I'll add them together. Simplifying gives me x to the power of 2 plus 3 is x to the power of 5. So you can use either of these two approaches. If you're comfortable using the meaning of exponents and you want to think of it this way each time, that's absolutely fine. You'll get to the answer. If you want to start practicing using the property of exponents, this helps us speed it up a little bit. But they'll both give us the same answer, so it doesn't matter which one you use. And you might use a slightly different approach depending on the circumstance. And we'll look at a number of examples where we use these properties. So what's going on in our second property? Well, here we only have one base, a, and it's raised to the exponent m. And then all of that is being raised to a second exponent n. What are we being told to do with these exponents? Well, this time we're still only going to write the base once, but we're going to multiply our exponents together. Let's look at an example. Let's say we have x to the power of 3, and then I'm going to take all of that and further raise it to the power of 2. Again, in this column, I'm going to look at what this means by thinking about what x to the power of 3 is really telling me about x. Okay, well, it's really telling me that x is multiplied by itself 3 times. And outside the brackets, I'm still going to raise that to the power of 2. But what does that power of 2 mean? The power of 2 simply means that everything inside the brackets here is multiplied by itself twice. So I have x times x times x, and I'm going to multiply that by exactly the same thing, x times x times x. Similarly, we could have written x to the power of 3 times x to the power of 3, and that tells us what the 2 is all about, and then expanded it to give this line. So what's going on here? What we really have is all of these x's being multiplied by all of these x's, and we could just as easily write that without the brackets. So we have 6 x's all multiplied together, which is much easier to write as x to the power of 6. It gets a little bit long, so that's why we have these properties. We have these shortcuts. Again, 5x to the power of 3, and in brackets, all of that is being raised to the power of 2. My property tells me that all I need to do is multiply m times n, the two exponents. In our case, 3 times 2. So this is really x to the power of 3 times 2, and 3 times 2 is 6. Again, feel free to use the variation that you're most comfortable with. Next, we'll look at what happens when we divide bases that are themselves raised to exponents. The two properties in the table here are identical. We're just going to look at two different cases. In the first, I'd like to look at what happens when m is the larger number. In other words, when m is greater than n. And in the second case, I'd like to see what happens when n, the exponent in the denominator, is the largest number. In other words, when m is less than n. We'll also look at the case when m is equal to n. In other words, when the a's are raised to the same exponent. Another caveat we need to add to these properties is that in neither case can we have a being equal to 0. We're not allowed to divide by 0. It's impossible. So these rules do not apply where we have a mathematical impossibility, where a is equal to 0. In any case, as before, let's have a look at an example. So what happens if we have x to the power of 3 divided by x to the power of 2? Well, once again, look at what this means. In the numerator, we have x multiplied by itself 3 times. And in the denominator, we have x multiplied by itself twice. And what are we allowed to do when we have the same thing in the top and the bottom? Well, as long as the pieces are being multiplied in the numerator and multiplied in the denominator, not added or subtracted, only multiplied. If we have the same thing in the numerator and the denominator, we can cancel those. So we can cancel one pair of x's from the top and the bottom. In fact, we can cancel a second pair of x's from the top and the bottom. And all we have left now is a single x in the numerator. In other words, the final answer is x. You can think of it this way. In the numerator, we have x left, but what do we have left in the denominator? Well, in the denominator, it's not that there's nothing left or 0 left. There is still a 1 there. Remember that there's always an invisible coefficient or an understood coefficient of 1 in front of any variable. Of course, if the only thing in the denominator is a 1, we don't bother to write it. So we write x over 1 as simply x. So we could absolutely come to the same conclusion using the property. Same question, x to the power of 3 divided by x to the power of 2. Well, our property tells us that we are absolutely allowed to divide these as long as the bases are the same. X and x, they are. And if that's the case, we only have to write the x once, the base once. And now we'll take m and subtract n. In other words, we'll take the top exponent and subtract the lower one. So we'll take the 3 and subtract 2. So we have x to the power of 3 minus 2. 3 minus 2 is 1. Of course, we would write that as x to the power of 1. We would write that as simply x. So we, once again, get to the same conclusion. And you can use whichever one you prefer. So again, we're working with the same rule, but I'd like to have a look at what happens now when the exponent in the denominator is the larger one. So for example, if I have x to the power of 2 divided by x to the power of 3. So we have 2x's multiplied in the numerator and 3x's multiplied in the denominator. Because we have multiplication in both top and bottom, we can absolutely cancel as long as we have the same factor top and bottom. So we have this pair of x's that we can cancel, and a second pair of x's that we can cancel. As a quick aside, when I'm canceling, what's really left behind? Well, when I'm taking x and dividing it by x, I leave a 1 behind. So really what I'm doing is I'm dividing an x out of the top and an x out of the bottom. There's a 1 left in the top and a 1 left in the bottom. For the second pair, I'm dividing the top by x and the bottom by x, so there's a 1 left behind. So what's left in the numerator? 1 times 1 is 1, but we see that the x's are gone. Where is our x, our leftover x? Well, it's in the denominator. And there it is. So when we use the property of exponents, what does the second question look like? So it's the same question, x to the power of 2 divided by x to the power of 3. And our property again tells us that as long as the bases are the same, I only have to write it once, and I will still subtract the numerator, or rather the denominator from the numerator. I will take the numerator and subtract the denominator. I will take the top exponent and subtract the bottom exponent. So in our case, we have 2 minus 3. What's 2 minus 3? It's negative 1. You've probably realized that negative exponents are something we're always going to rewrite. What does a negative 1 tell me to do with the x? Well, an x raised to a negative exponent always means take the reciprocal. So I'm going to rewrite x to the power of negative 1 as 1 over x. So you see, again, we get to the same point. Sometimes an easy way to think of this problem is to say, well, in which part of the fraction, the numerator or the denominator, do I have more x's? For this second question, I have 3 x's in the bottom and 2 at the top, so I have more x's on the bottom. So once I've canceled all the x's, I should have x's left over in the denominator. In the previous question, where we had more x's in the numerator to start with than we do in the denominator, once I've canceled all my x's, where should my leftover x's be? Well, they should be in the numerator, and that's exactly where our answer is. One additional piece I'd like to look at is what happens when m and n have the same value. For example, what happens if I have x to the power of 2 divided by x to the power of 2? So actually, I'll write that over here using the meaning of exponents. So x to the power of 2 divided by x to the power of 2 just mean I have x times x, top of the fraction, and x times x, the bottom of the fraction. 1x from the top and 1x from the bottom cancel. I've got another pair from the top and the bottom I can cancel. What do I have left? Well, in the numerator, I have 1 times 1 is 1. And in the denominator, I have 1 times 1 is 1. 1 divided by 1 is just 1. So x squared divided by x squared is just 1. And we use that just by looking at what exponents really mean and canceling the x's. We'll get exactly the same answer if we use the property of exponents. So again, x divided by x means, well, we're allowed to do that, and we'll write the x only once. We'll take the top exponent and subtract the bottom exponent. So we get 2 minus 2. What is 2 minus 2? 2 minus 2 is 0, so our answer is x to the power of 0. What is x to the power of 0? Well, if you remember from our initial discussion, this means that there are no x's being multiplied together, and we just have a 1. So we do get the same answer here as well, and it's another way to look at why x to the power of 0 is equal to 1.
And finally, we'll see what happens when we have more than one variable or simply more than one factor. So these could be variables or they could be normal. And finally, we'll see what happens when we have more than one thing. So more than one variable, or perhaps something like a 2 and an x inside of the brackets. So in the first property, we look at what happens when the factors are multiplied, so when these variables are being multiplied. And in the second property, we'll look at what happens in division. So again, this could look something like this, 2 over x raised to the exponent. And we'll start with exactly that example. So we have 2 times x, and all of that is being raised to the power of n. We can think of this in a couple different ways. Sorry, I don't want to say power of n. Let's actually give that a number. We want to say, what if it's raised to the power of 3? Okay, so we know that if we write the 2 and the x next to each other, we mean that they are being multiplied together. But you could separate them and write them as 2 and then the multiplication sign or a dot x. And all of that is raised to the power of 3. So again, if we look at what does it mean to be raised to the power of 3, well, everything that's underneath it, the whole base, the 2 and the x, are multiplied by 2x 3 times. by themselves. So what we have is 2 times x times 2 times x times 2 times x. Now those dots are a little bit excessive. We don't need quite so many, but I wanted to make it clear that we have everything inside the brackets multiplied by itself 3 times due to the exponent of 3. Do we really need those brackets? No, we don't. This is really just 2 times x times 2 times x times 2 times x. And we could write that as 2 times 2 times 2 and x times x times x. The order of that we multiply in is not important. And 2 times 2 times 2 is 8. And x times x times x we know is easier to write as x to the power of 3. So that's fairly long-winded. Here, using the property of exponents is usually much easier. So we have the same question, 2x to the power of 3. What the property tells us is that every single thing inside the brackets, the a and the b, are raised to the power of n. So a is raised to the power of n, here it is, a to the power of n, and b is raised to the power of n. Here it is, b to the power of n. So in our case, we're going to take both factors, the 2 and the x, and raise them to the power of 3. So 2 to the power of 3 is our first piece, and then we take x and also raise it to the power of 3. Of course, you don't need to draw those arrows, but I'm trying to demonstrate what my thought process is. And 2 to the power of 3 is 8. We should evaluate anything that's easy to evaluate. And x to the power of 3 is already in its simplest form. The process when we've got a quotient, so when we're dividing, is very, very similar to that of this multiplication property. So, for example, if I've got 3 over x, and all of that is raised to the power of 2, let's see what happens. Well, if everything's raised to the power of 2, that means everything here, 3 over x, is multiplied by itself twice. So we have 3 over x times 3 over x. Do you have to remember how to multiply fractions? Maybe it helps us if we write this instead of with brackets, we write this using a multiplication sign or a dot. In any case, to multiply fractions, we're going to multiply the numerators and then separately multiply the denominators. So we get 3 times 3 is 9, divided by x times x is x squared. Once again, it's usually easier to use the property of exponents rather than work this out using the meaning. So again, let's start with 3 over x to the power of 2 and have a quick look at what our property tells us. Well, it says take every single thing inside the brackets and raise it to the exponent, right? So we take the entire numerator, a, and raise it to the power of n, because it's a to the power of n. And then we take the entire denominator, the b, and raise it to the power of n. And here is our new denominator. So if we apply that here, we have 3 to the power of 2 in the numerator and x to the power of 2 in the denominator. We can work out 3 to the power of 2. 3 to the power of 2 is 9. So we do want to evaluate anything that's easy to evaluate. We can leave x to the power of 2 as x to the power of 2. Now we'll look at a series of examples where we use all of these properties. Certainly we'll use several properties in every question, and that will really help us to solidify how to use the properties of exponents and how to manipulate questions that have exponents in them.